So this project is mainly designed to apply our knowledge on machine learning foundation, the course what we have, to understand the different models, what is being used, and how we can use that, and how to evaluate the model, and then ultimately learn the lesson from creating a model and training the model and evaluating the model, and then ultimately deploying the model. So let's get started with it. So in this project, we have given a project to build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery steam generator to generate power. In this project, we have given around 9,568 hourly average ambient environmental readings from different sensors at the power plant, which will be used to model create the model. And in the data, what I found, the data is very clean, which is very highly unlikely in the normal setting. There will be some data cleanup would be needed. The data engineers would be doing that before and then giving the data to data scientist. Now, coming back to the problem, what we have, so as we can see, there are around four features, which is basically independent variable, and the dependent variable is the net hourly electrical energy output, which is our point of interest to predict that value depending on all these four different features that we have. Now, when I looked at the data, so these are the things we are trying to get out of. First thing we would do is exploring the data, then define the feature set, then develop the model, and then evaluate the model, and then selecting the best model what we can think of based on the error and all other things what we normally look at before we zero on a particular model. So when I explored the data, as I mentioned before, that there was no data missing. All the data is clean, and so basically we can use the data to start creating the model. So before we start creating the model, I have separated out at least 80% of the data for making the model, creating the model, and rest 20% of the data for training and for evolution and test data. So basically 20% we can split it into 10-10 so that we can fine tune, and then ultimately we can use that fine tuned model and see how the test how the data, how the input is going to behave with the fine-tuned model. So when I run the regression first time with all the features in, as you can see here, ATV, AP, and RH, all of those features are actually plugged in to predict the output of the power plant. As we can see here, this is really awesome to see the result. R-square value is close to 1, and the standard error is 4.5, which is really good. But when I dig deeper, and also I have done some residual output, as you can see on the right-hand side corner, the variations are really close to the actual output. Based on the predicted PE and the residual value, you see the difference is very small, in a way that our predicted data is very close to the actual data, what we have from the actual output of the result. Now, when I was doing the regression, this is the first time I'm running the regression with all the features, but then I did take into consideration other features like one at a time. Let me see if it can move. Okay, so here we see I just ran the regression to predict the output for PE, only taking AT, which is ambient temperature, into consideration. So in this also I see it's really good prediction, which only AT, if we consider feature AT to predict the output of output for the power plant, it is actually giving a very good result. As you can see, the standard error is only 5.4, and R-square value is close to 9.9. So in a way that this is a very good indication, or AT is highly correlated with the output of the energy output for the power plant. Now, if you look at the other one, AP, which is ambient pressure, Not so much. The standard error is way too high, 14.5, and R-square value is 0.2. It's very, very low. So with the change of AP, there's not much of change in output. So we can basically discard this model. We cannot use this. Next one is RH. The same thing with this relative humidity also. As we can see, R-square value is very low and the standard error is really high. So we cannot use this model to predict the output. Now we look at the V. It seems to be very close. As we can see, the R-square value is 0.7 and the standard error is 8.4. However, when I'm looking at the data, the residual values is really going high sometimes. As you can see here in the number 3, it's went up to 16 point something as a variation. So this one, yes, it is close enough that it can also predict the output, but there are a lot of variation in it. When it comes out, the residual values are really high for some parameters, some values. So, and then what I did again, I ran another regression with AT and V, as to see how good this model could be. So when I ran these two things together, and it's a really good result here. As you can see, the standard error actually reduced to 4.9, and the adjusted R square is 0.9. So it's a really good result. What I can see that I ran like 4 or 5 regressions based on the different features. Yes, we can, if we want to run all the feature set, all the features, like 4 features together to predict the power output, definitely we have a model there, but maybe we can save some computational power if we just want to use 2 features instead of 4, because other 2 features are not contributing too much. So we can use this model to predict the output. Now, why do we use the linear regression in this case? Because here we are using this model to predict the output for the power plant. So we have used a linear regression. Again, we can use some of the other models, but again, I need to explore a little bit more on the Google Cloud. I did try, but somehow it did not work out quite well. So I just went back to the basic Excel sheet regression. And I think I got a good result on this. Now, in conclusion, what I can say is that the linear regression model actually worked out fine in this case. But in the real world, most probably we will have more complicated settings where we'll have thousands of different features, and maybe we need to consider some other parameters. Maybe you have to combine the decision tree or linear regression somehow fuse together, or we can use a linear regression output to be input to the other model. So in the real world, it could get complicated very quickly. So I'm looking forward to learning more. So in the next project assignments, maybe we'll get to use those intensively. Thank you very much.